The energy needs of our brains are primarily supplied by the sugar glucose. This glucose will commonly come from the various carbohydrates that we eat that are then digested and broken down into glucose, which will then freely circulate through our bloodstream. However, between meals, our body will often have to produce extra glucose in order to continue to feed the brain. Now, the liver does this using a process we call gluconeogenesis. And as part of this process, we need to take smaller organic molecules and combine them together to make our larger molecules that will eventually become glucose. So one of our key reactions is shown here. We're taking this 3-carbon molecule here. We call this dihydroxyacetone phosphate. We're combining that with this glyceraldehyde 3-phosphate, and we're producing a new carbon-carbon bond linking these two together. This is our fructose 1,6-bisphosphate that eventually becomes our glucose. Our glucose also contains 6 carbons, similar to this fructose molecule shown here. Now notice we're forming a carbon-carbon bond here. And again, this is something that can be somewhat challenging in organic chemistry. Normally when we've done this, we've used things like organometallic compounds, where we're able to create a nucleophilic carbon that then attacks another electrophilic carbon in order to form that new carbon-carbon bond. As we look at these two molecules here, you'll notice that we don't really seem to have any obviously nucleophilic carbons. Right? In fact, we have a lot of oxygens that are going to be pulling electron density away from those carbons. And so you might think all of our carbons here would be very electrophilic. How can we manage to form that new carbon-carbon bond? Well, the answer comes through some unique new functional groups of our enols and our enolates. And these are actually going to use the inductive effect of our carbonyls to pull electron density away from our carbons, but also away from the nearby hydrogens on our carbons. Right? So our carbonyl is pulling electron density towards itself, and that inductive effect also means that we're pulling electron density away from these hydrogens, and that means that these hydrogens then become more electrophilic and become a target for bases. Or in other words, the acidity of our carbon here, or the hydrogens attached to our carbon, is increased due to the inductive effect of our carbonyls. The increased acidity of these hydrogens here allows us to deprotonate these hydrogens and create an anion here at our carbon adjacent to that carbonyl. That anion, of course, will then mean that our carbon is nucleophilic and will enable it to react and form this new carbon-carbon bond. Once we deprotonate it, we formed that carbanion, which is going to be our enolate functional group, whereas our enol is just the protonated form of that same functional group. So let's start by looking at a simple carbonyl here. This is our ethanal with our 2-carbon aldehyde here. If we bring in a base, we can use that base to, again, remove one of these hydrogens. Again, the acidity of these hydrogens is increased through that inductive effect. We're pulling electron density towards our carbonyl, and that reduces the electron density of our actual hydrogens. So these extra electrons will then come in, and we form a double bond between our carbons, and our negative charge moves up onto our oxygen. This right here, our resulting product, is our enolate. So we now have a negative charge here. We have our double bond of our carbon, right? That's indicating the increased electron density around that alpha carbon right here. Again, alpha just refers to the carbon next to our carbonyl carbon. This enolate, of course, also has another resonance contributor where we can move that negative charge down and put it on our carbon itself. This is actually going to be our minor resonance contributor because the negative charge is on our less electronegative atom. But it's a helpful resonance contributor because it shows us that our carbon does indeed have a higher electron density than it originally had in our carbonyl. Now, if we take our enolate here and protonate it with acid, so we have our hydronium ion here representing our aqueous acid. We pull off a proton, and this creates our enol, which is just our acidic form of our enolate. Now our enol here you might recognize, so we saw enols before as the initial product of our hydration of alkynes. And then our enols, of course, can rearrange to our ketones or our aldehydes through tautomerization. So we refer to these as tautomers. Tautomers are just isomers that can easily be converted back and forth. So our enol will tend to form in acidic conditions. Our enolate will tend to form in basic conditions. However, it is important to realize that these are very reversible, right? So there's actually going to be an equilibrium between our ketone form or our aldehyde form and our enolate or our enol form, right? So with acid, we can convert back and forth between our enol and our carbonyl form. And with base, we can convert back and forth between our enolate form and our carbonyl form. In most cases, the equilibrium is going to favor our carbonyl, right? So that's what we saw with our alkyne. We would form that enol initially, and then it would rearrange to our carbonyl. So we're going to have an equilibrium between our enolate or enol forms and our carbonyl form. Now this equilibrium is going to be influenced by the structure of our carbonyl compound. For things like esters, it's going to be strongly favoring our carbonyl form. So our ester here, of course, as we've seen previously, we have resonance between our two oxygens that then stabilizes this carbonyl form and reduces the acidity and likelihood that we're going to deprotonate here to form our double bond. Of course, our aldehyde or ketone forms that we've already seen will be somewhat in the middle. And the compounds most likely to form enols or enolates are going to be compounds that have dicarbonyls. So if we have two carbonyls, right, these will both exert their inductive effect, and our carbon here in the middle between those two carbonyls will have a much more acidic hydrogen to easily lead us into that enol or enolate form. Again, of course, as with our alkynes, right, this is still a weak acid. It's just that it's much more acidic than a carbon-hydrogen normally would be. So our overall trend here for our enol and our enolate equilibriums is esters least favorite the enolate or enol form, followed by ketones, aldehydes, and then our dicarbonyls. Dicarbonyls, of course, can come in various forms. You can have ester dicarbonyls, ketone dicarbonyls, or aldehyde dicarbonyls. Those would follow the same general trends, right? So all of our dicarbonyls favor the enolates and enols more than our single carbonyls. But again, ester dicarbonyls would be least favored of all of our dicarbonyls. Okay, so we've successfully formed our enolate. Now, how does this lead to the formation of carbon-carbon bonds? Well, as we've seen, so our deprotonation here resulted in this double bond that also resulted in our carbon itself having a higher electron density. Now, within our solution, right, we're never going to have just one molecule of our ethanol, right? So we could draw a second molecule of ethanol over here, And of course, this is a carbonyl, so it's going to be pulling electron density towards itself, creating a partial negative charge on our oxygen and a partial positive charge on our carbon. That carbon, as we know, is a good electrophile that is susceptible to nucleophilic addition reactions. So if we take our enolate, here we have a nucleophilic carbon. We just need to move our electrons down from our oxygen to give way for our electrons here of our double bond to attack. And we'll attack this electrophilic site of our carbonyl here. So we're actually attacking with the enolate form of our ethanol onto another molecule of our ethanol. Again, as always in these nucleophilic addition reactions, the electrons from our double bond move out of the way up to our oxygen. So the product here, we would have our enolate, which now has gone back into its carbonyl form, and we formed a new bond, which again I'll highlight in purple, over to our second molecule of our ethanol, which now is in the alkoxide form. So there's our initial product, and then of course this can get protonated by perhaps water if we are in an aqueous environment to result in our aldol addition product, as we call it. So this overall reaction we call an aldol addition reaction. So with our aldol addition here, we've added together our aldehyde and formed a new alcohol. Right? So you can think of that aldol as referring to the aldehyde and the alcohol that we formed in our reaction. And of course these are both coming from just individual molecules of our original aldehyde. Right? We had one aldehyde attacking the other aldehyde, using the nucleophilic nature of that alpha carbon here. So there's our alpha carbon. This would be referred to as our beta carbon, the carbon that's 2 carbons away from our carbonyl. So we always get a beta hydroxy carbonyl in our aldol addition reactions. Right? So you always have this characteristic pattern of a carbonyl, and then 2 carbons away you have that alcohol. Notice here, of course, this also follows a similar pattern to the previous nucleophilic addition reactions we've seen with carbonyls. Right? Normally when we attack and form the new carbon-carbon bond, such as with our organometallic compounds, we always end up producing an alcohol from our original carbonyl. Now, as with the formation of our enolate itself, these addition steps are also reversible. So we will have an equilibrium here between our original carbonyl, our enolate, and of course our final aldol addition product. For aldehydes, the equilibrium will tend to favor our aldol addition product here in the presence of our base. For ketones though, we're going to be getting more crowded then at that point, right? So if we had a ketone here, that means we'd have at least one extra carbon attached here, at least one extra carbon attached here, and of course that makes our nucleophilic attack here much more difficult. So as always with our nucleophilic addition reactions of carbonyls, ketones are going to be harder to react, and their equilibrium will tend to favor the carbonyl form as opposed to that aldol addition product. Now, one of the things you might notice here with our aldol addition product is, of course, we still have a carbonyl, and we still have an alpha carbon that is going to be more acidic because of the inductive effect of that carbonyl. So we don't necessarily have to stop at this initial aldol addition product. So we can continue with what we call an aldol condensation. And this will occur normally when we have high heat. So our aldol addition will often occur at lower temperature. Aldol condensation will occur at high temperature. Okay, so to see what happens here, first we need to take our initial product and we're going to form a new enol from our initial product here of our aldol addition. So I'm going to bring in my base again and deprotonate here to form my enolate. So I'm showing my major resonance contributor again with a negative charge on my oxygen. Now from here, so you might think we could then try to do another aldol addition reaction, but instead what we're going to do is we're going to move our double bond over and actually kick off our hydroxide ion here from our hydroxy group. So this is a rare example of a dehydration occurring with hydroxide instead of water, right? Normally we have to protonate alcohols in order to make them good leaving groups, but in this case we're actually kicking it off as our hydroxide ion. So we recreate our carbonyl here on the left. Our double bond shifts over to where that hydroxy group used to be, and of course we still have our final carbon there. So again, it's a dehydration because we're eliminating hydroxide ion. And of course, we're then forming a double bond. This compound here has a alpha-beta unsaturation, right? We refer to unsaturated hydrocarbons as hydrocarbons that have carbon-carbon double bonds. Here our double bond is at the first and the second carbon after our carbonyl, which we refer to as our alpha and beta sites. Now you might remember from last semester, right, that when we have double bonds sitting next to each other, these can be conjugated, which leads to increased stability, right? So this will be a conjugated system here, which of course is what drives this overall aldol condensation reaction. Right? So by eliminating that hydroxide, we're able to create this double bond that's then going to be conjugated and stabilizing our carbonyl over here. So our aldol addition reaction will be favored at low temperatures, and then we can push this forward with high temperatures to get our aldol condensation product. So we could get either that beta hydroxy carbonyl, or we could get our alpha-beta unsaturated carbonyl. So far, we've only looked at a reaction between one aldehyde and an enolate formed from the same aldehyde. What happens if we try to combine two different carbonyls, similar to that biological reaction that I showed earlier? Right, so here we have propanol and butanol, and I'm going to add them together with base and at low temperatures, so I favor that aldol addition reaction. So we might say, okay, we'll form our enolate here from deprotonating. So this guy could get deprotonated to form my enolate, and then this enolate would attack my carbonyl over here, and I would end up producing, so I would have my first carbonyl with my 3 carbons, and then that attacks the other carbonyl from my enolate site. So my new bond forms right here, leading to the alcohol and of course the 4 carbons of my butanol. So that looks relatively straightforward and simple, right? However, you might ask, how did I decide where to make my enolate? right? So I kind of arbitrarily decided to make it here, but I could also make it right here, right? So I formed that enolate, but I could also form this enolate here, right? And then this enolate could attack that molecule, and that would lead to an entirely different product, right? So if those two reacted, our carbonyl now would be longer, so we'd have our 4-carbon carbonyl, and that would be bonded to our 3-carbon carbonyl that becomes the alcohol. A completely different product compared to our original reaction, just based on which enolate attacked which carbonyl. Of course, again, following my same reasoning from earlier, right, there's always going to be multiple molecules of my propanol here, and so this enolate could react with another molecule of my propanol, right? So in that case, that would lead to one molecule in the carbonyl form bonded to the other one in my alcohol form. Or again, I could do that between my enolate form of my butanol and my carbonyl form of my butanol. So in that case, I would get my 4 carbons from one carbonyl bonded to my 4 carbons of the other carbonyl, but now it's converted to my alcohol again. Which of these products would I form? Right? I have shown 4 different possible products. How would I decide between these? Well, the answer is I wouldn't. If you try to do a mixed aldol reaction like this, you'll get a confusing mixture of products. Right? None of these is particularly more or less likely. You might have slight differences in the percentages of each of these, but you'd end up with just kind of a big mix, a big jumble of these different products. So in general, we want to avoid these sort of mixed aldol reactions, right? This sort of jumble of products is rarely useful for anyone. So is there any way to perform a useful mixed aldol reaction? Well, as it turns out, there are a couple of different mechanisms we can use. The first possibility is to use a catalyst that can control which of our enolates forms. This is the biological approach, right? So in that reaction I showed you earlier that's leading towards our glucose, we use an enzyme catalyst to specifically hold our molecule and only allow one to react into our enolate while the other stays in the carbonyl form. Another possibility, though, is to use a non-enolizable reactant. So if we take this carbonyl here and react it with another carbonyl, so here we have our carbonyl attached to a benzene ring. Over here we would have our 2 hydrogens, which of course could be deprotonated to create our enolate. Over here, we would have 1 hydrogen here, but as we look at our carbon here, it already has 4 carbon-carbon bonds, and so we don't have any hydrogens here on this particular aldehyde. So this is non-enolizable, which means that in our reaction, we're never going to have this reacting as an enolate attacking this aldehyde over here. So this will always be reacting to form our enolate. And then, of course, this enolate can attack our aldehyde over here and create our Aldol Addition product. So again, we'd use our base at relatively low temperatures, and we'd create our Aldol Addition product. We have our enolate, which stays in the carbonyl form, and our new bond to our other carbonyl, which now is in our alcohol form. And of course, this would still have our aromatic ring attached. We could have some competition from this enolate attacking other molecules of our propanol over here, but it's going to be much less competition than with our previous mixed aldol reaction, where we had 4 different possible products competing. We can also, of course, change our concentrations in order to try to favor the reaction of that enolate with our non-enolizable carbonyl instead of reacting with another molecule of our propanol. Another possibility for controlling our aldol reactions is to use a directed aldol reaction. Now, what we mean by this is we're going to take a carbonyl compound. Here I'm actually going to use a ketone. And we're going to first add a very strong base. So in this case, I'm going to use lithium diisopropyl amide. So this is a very large and strong base compound. We have 2 isopropyl groups bonded to a nitrogen with a negative charge. Our lithium there is just acting as a positive counter ion to our nitrogen strong base. Now with our LDA here, this is a very strong base, but it's also crowded. So this strong base is going to react with our ketone over here. It has 2 different places where it could react. Right? We have alpha hydrogens on either side of our carbonyl carbon here. We could attack on the right side, but notice we're relatively crowded over here. So instead we're going to want to attack over here on the left side where we have a lot more room. So we pull off this hydrogen and form, we call this the kinetic enolate. Right? The kinetic product is the one that's favored due to the crowding and the steric hindrance, whereas the thermodynamic product would be the more stable product. In this case, with our very strong base and crowded base, we're going to favor that kinetic product. So we again get our enolate formed over here on the left. And again, because we have a very strong base, this isn't going to be an equilibrium the same way that was when we added our weaker base with our normal aldol addition reaction. Right? So with the strong base here, we're going to essentially convert all of our ketone to our enolate, and then we can just take this enolate and put it in solution in a second step with our particular carbonyl that we want to react with. So let's say I add it together with my propanol that I was using above. And now we don't have to worry about what enolate will form, right? Because we already formed our enolate by adding this very strong base, right? So we form our enolate first in a separate step. So this will be step 1, forming our enolate. And then step 2, we take our enolate and add whatever carbonyl we want to react it with. And now we know exactly what's going to happen because we already have our enolate formed. So we'll take our nucleophilic carbon, attack that electrophilic carbon of our other carbonyl. Our electrons move out of the way, and we make our Aldol addition product. So in this case, we'd have the carbon structure of our ketone with the new bond forming over to our aldehyde in this case, which becomes our alcohol in our product. In order, of course, to get the protonated alcohol, we would have a third step where we add acid or water to complete our reaction. We can essentially look at this directed aldol reaction as a third means to control our mixed aldol reactions. Right? So we are still doing a mixed reaction, right? We're using 2 different carbonyls. It's just that, again, we're using that very strong base to make our enolate first and then add it to our carbonyl afterwards. So our three key approaches, again, we could use an enzyme that would control what enolate forms. We can use a non-enolizable reactant so that we know, again, for sure what enolate will form. Or we can add our base first and make the specific enolate that we want before we start our aldol addition reaction. So as we see here, our enolates create a unique new nucleophile that can be used to react with our carbonyl compounds. Now, so far we've just looked at enolates with our aldehydes and our ketones, and then using those to add these together to create our unique aldol addition or aldol condensation products. Now, as we saw earlier, enolates can also form with other carbonyl-based compounds, such as esters. In our next lecture, we'll be looking at some of the reactions that can occur with ester-based enolates instead of our aldehyde or ketone-based enolates.